Welcome to class number 7, session number 2. This session will review the different methods for the fabrication and the synthesis of the carbon nanotubes. Most of the methods for synthesis of carbon nanotubes require supporting gases and vacuum. Few examples for synthesis of carbon nanotube include chemical vapor deposition, inductively coupled plasma, and laser ablation and carbon arc processes. Gas phase methods are volumetric, and hence they are suitable for applications such as composite materials that require large quantities of nanotubes and industrial scale synthesis methods. One of the disadvantages of gas phase synthesis method is low catalyst yield, where only a small percentage of catalysts form nanotubes. We have learned in the previous class about the use of CVD for growth of nanowires. Many of the details of this process can be projected on the CVD growth on the carbon nanotubes with some modifications, of course. So we will now briefly go over the CVD system in the case of the carbon nanotubes. Schematic description of the process is illustrated in the upper image on the screen. A substrate seeded with metal catalyst is exposed to a gas containing carbon. The system is then heated up to several hundred degrees Celsius until it disintegrates and single reactive carbon atoms are generated. A substrate containing metallic catalyst atoms is used as the active site for the carbon nanotube formation. Carbon nanotube grows below the metal catalyst, while the catalyst is still active and more carbon atoms are in reaction to form the carbon nanotube. The carbon nanotube synthesis usually takes place in a chamber as illustrated in the lower image. The main parts of the chamber are the gas inlet that are controlled with the flow of the carbon, which contain gas and nitrogen, and all of these together can be obtained within the same chamber as seen on the figure. Numerous parameters influence the carbon nanotube growth. One example parameter is the metal catalyst. The function of the catalyst in the CVD process is the decomposition of the carbon source throughout the plasma irradiation or heat, namely thermal CVD, as its new nucleation to form carbon nanotubes. The most frequently used catalysts are transition metals, primarily iron, cobalt, or nickel. Other parameters that will influence the growth of the nanotubes are the temperature, the mass flow rate, hydrocarbon source, and the carrier gas. Several modifications to the CVD methods for carbon nanotube growth has been proposed and used so far. Here are two of them, which you can see in the upper image on the screen. The first system is the extrusion or root growth. In this system, platinum is used to segregate to particle surface and to form an apron around a core of iron. It is assumed that under the prevailing reaction conditions, the composition of acetylene occurs predominantly on the platinum-rich region of the particle. It is suggested that transport of carbon throughout the catalyst take place as a consecutive process. Rapid diffusion throughout the platinum followed by slower diffusion throughout the iron components to be precipitated on the upper surface of the particle as a filament. The second system is tip growth. A mechanism has been postulated to account for the growth of filamentous carbon produced from metal catalyst decomposition of the acetylene. This mechanism involves the diffusion of carbon throughout the catalyst or the catalyst particle from the hotter leading phase, on which exothermic decomposition of the hydrocarbon occurs, to the cooler trailing phases at which the carbon is decomposed and deposited from the solution. Excess carbon buildup occurs at the exposed particle phase and is transported by the surface diffusion around the peripheral surfaces of the particle to form an outer skin on the filament. As indicated in the previous slide, numerous parameters influence the carbon nanotube growth. The lower figure on this screen displays the graphene growth mechanism that involves the decomposition of the methane hydrogen mixed plasma and the hydrocarbon radicals. The hydrocarbon radicals in the gas phase recombined with each other after they had floated for a certain distance, and the metastable carbon atoms and the molecules form the sp2 structure on the copper surface are illustrated. In this case, effective length for growing graphene between the plasma and the center of the hot zone can be examined. The optimal distance usually is in the range of 30 centimeters. CVD is one of the most promising synthesis methods for carbon nanotubes, although the quality of the nanotubes is often poor and the selective growth of either single-wall carbon nanotubes or multi-wall carbon nanotubes is not easily guaranteed. The orientation, alignment, nanotube length, nanotube diameter, and purity and density of the carbon nanotubes can be precisely controlled. An example of different types of carbon nanotubes are presented on the image in the present slide. The upper image presents a bundle of well-aligned nanotubes. The scale bar in this figure is 50 micrometers. The lower left image presents a TEM image of single-wall carbon nanotube. The scale bar in this case is 20 nanometers. The lower middle image presents TEM images of double-wall carbon nanotubes. The scale bar in this case is 2 nanometer. Similar to wrapping two sheets of graphene is exactly what we see here on the screen in the case of the double-wall carbon nanotube. The lower right image presents TEM images of multi-wall carbon nanotubes, and the scale bar in this case is 5 nanometers. And this multi-wall carbon nanotube is similar to wrapping 20 sheets of graphene. A different approach for synthesis of carbon nanotube is by electric arc discharge. This approach involves voltage applied between two graphene electrodes, as illustrated in the image, and of course all of this process involves high temperature. The synthesis in this approach is performed in a chamber filled with an inert gas. It could be either helium or argon. A difference of potential is applied between the two graphite electrodes cooled with water. The electrodes are then gradually approached until the distance between them is small enough to trigger an electric arc breakdown phenomenon. The anode is then sublimated, creating a plasma in the zone between the electrons where the temperatures can reach 6,000 centigrades. This is not enough for graphite to sublimate. During the sublimation, the pressure runs very high as carbon atoms are ejected from the solid. These atoms migrate towards colder zones within the chamber, allowing a nanotube deposit to accumulate onto the cathode. The type of nanotube that is formed depends critically upon the composition of the anode itself. This technique usually causes the growth of carbon nanotubes with the fewer structural defects in comparison with the other techniques. In this slide, you can watch a short video that illustrates the synthesis of the carbon nanotubes with the approach presented in the previous slide.
To obtain nanotubes, take 2 pure carbon graphite electrodes connected to a DC generator in an atmosphere of helium, an inert gas that does not react with carbon. At 4000 Celsius, the graphite fuses and matter torn from the electrode on the left is deposited on the right-hand one, forming nanotubes. After cooling, they can be collected from the freshly produced tip. There are hundreds of thousands of nanotubes here, so small that the knife doesn't damage them. Forming 90% of this powder, they are only visible through a microscope. This long structure spanning the screen measures about 5 to 10 microns in length for 10 to 40 nanometers in diameter.
Laser ablation is another technique for carbon nanotube synthesis. A pellet of graphite is placed in the middle of a quartz tube within an oven at controlled temperature. After evacuating the air in the quartz tube, the oven temperature is brought to 1000 to 1200 centigrades, and the tube is filled with an inert gas flow. A laser beam focused on the pellet vaporizes graphite by scanning its surface so as to maintain a flat and uniform surface. The carbon species produced by the sublimation of graphite are displaced by the gas flow, coalescence in the gas phase, and finally deposit on the cold copper collector. 2 approaches of the laser ablation method can be used. The one is called pulsed laser vaporization, or continuous laser vaporization is the second approach. The main difference between the continuous and the pulsed lasers is that the pulsed laser generates a much higher power density. The properties of the carbon nanotubes prepared by the pulsed laser deposition process are strongly dependent on many parameters, such as the laser properties, energy fluence, peak power, repetition rate, oscillation wavelength, etc., etc. Also, it depends on the structural and chemical composition of the target material, the chamber pressure, and the chemical composition, and other parameters that relates to the chamber itself. After their synthesis, carbon nanotubes can be functionalized as a way to improve their solubility and biocompatibility and to alter their cellular interaction pathways. Functionalized carbon nanotubes are promising novel materials for a variety of applications in the fields of chemistry, physics, electrical engineering, and biomedical engineering. The image presented on the screen shows schematics on the functionalization of the carbon nanotubes and on the ways how the functionalization can be achieved by using biomolecules, surfactants, polymers, and etc., etc. We reach now the end of class number 7, session number 2. Thank you.